Hello! Welcome to Optimizing Image Graphics, Memory, and Embedded UIs, part of our Embedded UI Live series. It's a long title. I like the title of Making Good Image Choices. It's a little bit simpler, and it's really kind of a focus of what we're going to talk about today. I'm Fletcher, Vice President of R&D here at Crank Software and one of the co-founders of Crank. This is an ongoing series. And today we're going to be moving from our conversation from last session where we were talking about different types of embedded UI memory scenarios, RAM, flash usage. And today we're going to expand a little bit on that, and we're going to talk about a specific use case about how rich UIs get built and kind of populated with images and graphics, and how you can get all that to fit in your embedded system. So just let's recap a little bit where we were last time when we were talking. We were talking about two different types of memory configurations, different types of memory use. We were talking about flash memory, and we were talking about RAM, dynamic memory. Flash is usually a very abundant memory in terms of a lot of memory available on the system, but because of its access characteristics, really favors reading content off of it, and so as a result, it's used a lot for storage. And your code, the data of the program, but not a lot for writing content. It can be used as a persistent store, but its access time is very slow for writing. RAM, on the other hand, very dynamic. All of your dynamic content tends to live in RAM. Content that you're accessing, reading, and writing very frequently, but it's more costly, and as a result, it tends to be in much more limited supply. So what does this have to do with the topic of embedded UI imagery? Right? What does that have, what's the relationship between those two things and bringing them together? Well, when we think about how embedded UIs are being created these days, we're talking a lot more about this shift of, moving from graphic primitives like fills, polygons, and rectangles to content that is really being crafted in design tools, Photoshop, Illustrator, Sketch. And that content then being handed off to an engineering team, typically for inclusion in your UI as a series of images, placement and content. So you're using these desktop development to graphic design tools to develop the static representation of the UI, and then the engineering team is taking that and then converting it into the product to a live representation. And that's where a lot of the richness is coming from. It's because these graphic design tools here are able to give us a lot of rich content, rich functionality that can be pre-processed and generated ahead of time. So, we've seen this coffee app before. So starting out in Photoshop, now coming into a storyboard environment, so our graphic design tool, or some other library of functionality that you're using to represent your embedded graphics. Of course, here we're going to talk about kind of the context we use in storyboard. Usually, what we're talking about when we're taking content out is we're talking about taking this imagery and it's going to be exported as a number of sliced images. So in this case, it might be a little difficult to see, but we've got this Photoshop content decomposed into 31 different images that are being used within our user interface. And that content is now being sort of positioned in place, shown, hidden, animated, alpha blended, composited together. All sorts of operations are happening with it. And that's all happening in the context of your design tool. So what does this all mean? Well, this represents a challenge. One of the things we talked about was this notion that our RAM, being a limited resource, is something that we typically will use for our display frame buffers. So I'm going to put this up here as our display. And really what we're talking about dynamic frame buffers. Now, we've got all these images that are sitting here in some sort of source format. And these might be PNG images or JPEGs or bitmap files, or they may even be raw images. There's lots and lots of different formats for how those images are stored. Most of those formats that we're going to talk about are encoded formats. They're compressed, and that's done so that they save space in the storage. We want to take this source and get it onto the display. Now, in an ideal world, we would just be able to take these raw images and move them over into the display. These raw images typically are organized, regardless of the format specifically, with some sort of header followed by the pixel data of the image. The header describes the type of encoding, the type of, the size and dimensions of the image, the nature of the color format, and it really tells us how we can get this data, sort of decoded and into the display, which is typically a pixel representation, right? There's lots of different encodings for displays as well. You can have palette-based, you can have 16-bit or 32-bit, but generically, at the end of the day, we're really representing colors in the display, so we need to kind of get these pixels across. Ideally, to move directly from source to display, we would have no problem. This is a read-only operation, so our source can sit inside of our storage, can go over to the display, and we'd be done. If only life were that simple. Because we're talking about a number of different image formats, we're talking about PNG or JPEG, BMP. These are encoded formats. So typically we have to run through some sort of decode process as we move our image source onto the image display. And this decode, now I'm going to take this arrow away, this decode phase is where the complication comes in. And this is where, sort of making good choices about where your images are, the type of image formats comes into play. Because our decode can really kind of be split into two different paths. If we have a raw format, or some like to say a direct image format, and that's to say that the data in this header is very closely related to the display content format, right? If that's the case, then when I come down this decode path, we can identify that this is raw data and push it in directly into the display. Now what's great about this is really all a read operation, which means it's perfectly suitable for content sitting in Flash. Flash access time for reading, very, very fast. Not as fast as RAM, but fast enough for us to be able to take the content and composite it onto a display, right? And this display is going to be sitting in RAM. What about this other path? What's going on here? So when we go through this other path, we are looking at really changing the format here, and usually we're looking at some sort of decompression, right? Where I need to take the encoded format, which is being shrunk down, and there's lots and lots of different types of encoding formats. There's lossy encoding formats, there's lossless encoding formats, there's complicated ones that are optimized for minimizing the footprint of the image. There's other compression formats which are optimized for decode speed. Regardless, this decompression has to go into a temporary buffer, right? So we're going to call this our scratch buffer. And this scratch buffer is really taking the place and giving us a place to expand the image into a native format or a direct format that we can push into the display. So once we go through the scratch buffer, we can take that scratch buffer and we can push it out directly to the display. Now there are some technologies, some hardware accelerators that actually will allow us to do decompression and push us out to the display kind of all in one stop. Specialized hardware can definitely help with this, but regardless, there's always a requirement to put this scratch buffer into RAM because we need to read and write from it. We'll read from it when we want to go to the ultimate display, but when we go and do the decompression, we're going to be taking these source bits of the image and pushing them out and writing them into a buffer. So we need that to be accessed relatively quickly. So this is a RAM cost here for us. So if I get a PNG image that I exported from Photoshop, it may be fantastic. I've got a very small footprint in terms of storage, but now in order for that image to get up onto the display, I have to go through this decompression phase. That's going to take a little bit of time, and it's going to take some memory. So what do we do? Typically, an engine or an application will look at this and say, let's minimize the CPU time that we're using for decompression. We don't want to go through and decompress that over and over and over again. So really what we'll do is we'll cache the results. What we'll really do is we'll cache the results to the scratch buffer. So the scratch buffer ultimately ends up being the full size of the image as it would be on the final display. And we do that so that we can circumvent this decompression stage and go directly out to the display after we've done a decompression of the image once. So now I get into resource management strategies around how big is my cache, when do I evict images out of it, what's the life cycle around this. A lot of complexity goes into this. And that's all so that we can have this balancing act between using RAM for images and being able to balance the storage costs. So this is sort of, kind of a generalized scenario when we look at it more specifically. So let's take a look at, what this type of scenario would look like if we had our Photoshop content and we were pulling that in. This is a tool that we have inside of our storyboard designer tool that allows you to actually decompose your scene, all of the images, and get a measure for both the storage cost and the live memory costs that are going to be incurred. So that Photoshop content that came in, you can see here we've got 31 files, 31 images that are going to be used. Now, not all those images are going to be live on every screen at all times. We'll have different modalities, so that's where a cache would come in terms of effectiveness. But you can see here, if I take a look at the number, right, we have uncompressed almost 3 megabytes of memory that's going to be required. If I'm working on a low-end platform, an MCU type of platform where maybe I've got a limit of 1 meg or 2 megs, and most of that is being occupied by my frame buffer, right? Our 272 by 480 by 272 display here, right, is using half a meg of memory on its own. Sorry about that. So we want to manage these resources a little bit. So what can I do in terms of judiciously choosing image formats to kind of shift that balance? Can I shift the balance from needing to do all this in memory, in RAM, or can I shift the memory to be the read-only flash memory? And so we can see what that would look like if I switch that balance. Storyboard gives you the ability to change the encoding of these source images that you're using within the design tool on the fly during the export process. And so as a designer and an engineer working together, what we can do is we can continue to build a rich user interface with all of these images, but then we can compensate and see how are we actually going to do the target resource management in terms of how much flash do I have, how much RAM do I have to actually operate with. And so if I change all of these images from being encoded images, that was the default when we brought them in from Photoshop, to being raw or direct images, and you can see here what we're doing is converting them all to be raw 888 pixels, right? So 24-bit. We can take this code path here. We don't need any of this RAM, so that 2.75 megabytes of RAM disappears right off of our metrics usage. And now what we can see is it shifts. It shifts into the storage costs. The storage costs go up. But the storage costs are one-to-one with what we'll use as our display costs. And because typically we'll have an abundance of flash, within reason, that's an okay trade-off. Now, there are other choices that can be made here. If we wanted to further optimize this, what we could do is we could look at a decode strategy that does allow us some level of compression, perhaps not as much compression as some of the more sophisticated compression algorithms, but gives us the ability to do a raw direct display. And so these are run length encodings, right? Run length encodings can be very efficiently implemented as if you're doing direct draws, because really it's a pixel color followed by a count. And so you can do these runs of pixel colors very, very effectively. So I can do that, and what I can do when I turn that on is you'll see that my storage costs drop dramatically. So I think our storage costs come down to a little below 2 megabytes, so 1.7 megabytes, right down. We've saved almost a megabyte by doing this compression, but we're not using any additional RAM because we're able to continue down this raw direct draw path, right? So these are choices that you can make in your design tool when you're building your embedded user interfaces on how do I manage the image resources. Now, we're talking as if my only choice is all in Flash or all in RAM. But there's a hybrid approach as well. Depending on the rendering technology that you're using, and Storyboard supports a variety of different image formats, you can mix and match these scenarios together. So what I can do is I can propose a hybrid solution. And my hybrid solution allows me to leverage the RAM that I have. Maybe what I've decided is in my system configuration, I can't fit all the images because I need a certain amount of dynamic memory for my display. I need a certain amount of dynamic memory for my variables and my stacks and my general heap, general operation. But I am willing to commit a certain amount of memory to cache. So I can put some of my content in Flash using a direct format, and then other content I can put into RAM, and I can decompress it and kind of maintain it here. Why would I want to do that? What's the benefit? Well, the benefit is even though Flash is perfectly suitable for reading in terms of access time, it is still slower than RAM. And so every image that's going to be composited, you're going to be reading through and running through those images. So if I can get a little bit faster access time from RAM, then by all means, that's what I'd like to do. The other piece that comes into this is our access time on Flash. When we're doing a lot of series of small little accesses, it's not always as fast in terms of the total throughput as it could be. So if I can put a larger image into Flash and get a long run of Flash read access, then I'm going to really hit my maximum performance on the Flash side, which is important, right? Because our total scene composition involves rendering a number of different images and compositing them together and putting them into this final display. So if I look now at this hybrid scenario, what I've done is I've gone through and I've identified individual images, the images that were really full background images or nearly full display images, and I've said, let's take those images and let's put them into Flash. And let's do the RLE encoding to keep their size minimal. And let's take the other content, right, the series of smaller images that we have, the series of pieces that are used in animations, little glows and pops and whatnot, and let's put them, leave them in their compressed format, and push them into RAM. Now that's not to say that you couldn't also put them into a raw format and put them into RAM, but that's a little bit wasteful because now I'm going to have the full image source here and the full image source here, and I might as well do that one-time decompression and put it into a cache, manage it that way. So today, what I really wanted to do is I wanted to kind of give you a little bit of a discussion point, a little bit of an overview on why it is that making good choices around the types of images that you're using, the image formats that you're using, can have a significant impact on your system. Embedded UIs today are using far more graphical resources than can comfortably fit entirely into RAM. Ideally, they can all fit into Flash in their native format, but even if they can't, we can compress them down. We can have a variety of techniques to essentially give us a lot of richness and a lot of variety in our user interface through the use of embedded images. Our next session, you'll see in this metrics display, we're talking about fonts. So in our resource calculations, today we're focused on images as a significant component in your Flash data storage. Our next session, we're going to be talking about fonts. We're going to talk about how fonts render, different display techniques, and we'll kind of run a similar scenario here to talk about pros and cons of different font technologies and different font choices that you can use in your embedded UIs to give you that richness of typographics. I'm going to take a look and see if we've got any questions. I've got a few questions here. So when it comes to UIs with animated screen transitions, how much does it impact the buffer? That's a great question. So there's probably two different ways to look at animated screen transitions. One is an animation where you're animating the content of a single display buffer, doing all that work, so constantly recompositing that scene during the animation, and then what you're doing is saying, okay, I'm finished with that, now I'd like to single step effectively and jump into the next screen, right? And in that case, what happens is, it's the same scenario, same cost as compositing one display. It's just you're doing an instantaneous transition at the end of your animation to the new display, and you're pulling in new content. So where's there a hit? Where's there kind of a bit of a cost? Well, for new images that may be compressed and need to be decoded, there's this decompression stage. And most UI technologies are going to give you a mechanism by which you can preload content. So if you know what's coming, or you know that there's a significant decompression cost, you can build that into either your startup time or mitigate it during the operation. Now, the second animation approach is to really animate two separate distinct screens or displays. And again, without getting into too much detail or specific to any particular hardware, there's lots of different ways to do that. Sometimes you can use two display buffers, in which case you would composite one display buffer, composite the other display buffer. All the same rules would apply in terms of your cache or your resource management. And then those two display buffers would actually be animated and moved together, right? So if you think of a fade in and a fade out, or you might be able to leverage hardware for that, in which case the hardware will actually work with the buffers directly and you won't have to recomposite the same. So it's kind of a scenario by scenario question, but in terms of overall costs, it's the same as if you had gone from one display to the next. And any sophisticated cache management strategy is going to take that into consideration and know essentially the context of your operation, know where you are, so that content that's being removed from cache ideally isn't immediately required back in the cache. There is another question here. Is there a general rule of thumb for the required amount of flash, RAM, and buffer size that you need for a UI application? It is a great question. There is probably no rule of thumb. There is some basic math that you can do. So frame buffers are probably the easiest. Your frame buffer requirements are going to be likely, sort of summarized as the width and the height of your display multiplied by your color bit depth. And here I'm assuming a scenario where we're doing direct draw. We're not palette-based. We'll have a whole other session when we talk about palette-based images and palette-based displays and kind of what the benefits and drawbacks are there. So if I'm looking at, what are we, 480 by 272 on our display? If I'm a 32-bit color, 24-bit color, so I've got full 888 for my RGB, red, green, and blue, I'm looking at, something just under 500K for this. If I go to 16-bit, so a 565 color format, right, 5 bits, 6 bits, and 5 bits for my red, green, and blues, I decimate the number of colors. I chop the frame buffer memory requirements in half, so that's a big savings. How does it affect the rest of your calculations downstream? Well, those calculations here depend on your source images. So you can decimate your source images, or you can decimate them as you decompress them, putting in the RAM. Ideally, if you're going into a raw format, they're going to be decimated at source. So what Storyboard will allow you to do is take a look at the sum total of all of your screens and give you a summary of all the resources used all together, as if everything was being used all in one shot when it comes to image resources, font resources, image script resources. It leaves the frame buffer display calculations up to you, because you might want to be single buffered, unlikely, double buffered, more likely, or even triple buffered in some scenarios. With that calculation and with that cost, sort of taken care of, now what you can do is you can say, well, that would be my ultimate high water scenario. But realistically, you have different screens that have different content on it all through it. It's unlikely you're going to be using all of your graphical assets all in one shot, all in one scenario. So instead, Storyboard Designer will actually break out the metrics for you, and we're not seeing it in our on-screen display. Oh, you can't see my display here. Sorry, width, height, and bit depth. I'm writing behind my pop-up. What you can't see is you can't see how much memory any individual screen is. So the Storyboard gives you that ability to sort of identify, here are the resources that are used on various screens, so that you get a better idea of, here's my ultimate high water mark, and then here's really my realistic operating high water mark in terms of a screen-by-screen basis. And it looks like that's our questions for today. Thank you very much for tuning in to our Embedded UI Live series. Hopefully you learned something, you took something out of it today. As I mentioned, our next session, I think we're going to talk about fonts. We're going to talk about font rendering and how it fits into this flash, RAM, memory management, and resource management story. Thank you very much for listening.